online seminar. Today it's our great pleasure to have Azadeh Moradinezhad from the University of Geneva. And she's going to talk about late-time universe as a probe of cosmic origins. Please take it away.
Okay, thanks, Julian, and thanks for the invitation. It's very nice to have the opportunity, albeit in this quite complicated times. So what I would like to tell you today is kind of a collection of different, seemingly different topics, but all with the underlying theme of using large-scale structure in the late-time universe to probe physics of inflation and the origin of cosmic fluctuations or primordial fluctuations. So, sorry, let me see. Okay, so let me just start with this picture that we all have seen, but just to give you an overview that in the standard scenario, sorry, I'm having a bit of trouble going forward. Okay. So we know that in the standard paradigm of early universe, during very early stages of the universe, we had a phase of accelerated expansion where the seed of fluctuations that gave rise to all of the structure in late time were set by quantum fluctuations of the inflaton field. A large fraction of our understanding of the early universe comes from observations of CMB, which is a snapshot of the universe when it was very young. And furthermore, at lower redshifts, we can observe distributions of galaxies and quasars, as is done in galaxy surveys. And in the current generation, we can our surveys go up to redshift about 1. And in the near future, we expect surveys of like Euclid and DESI LSST to push this redshift range to about redshift 3. And in between, in addition to individual sources, we can also probe the large-scale structure via observing fluctuations in the intensity of emission lines. And the most familiar one for most is probably 21 centimeter line, which in your group, of course, there is a significant amount of work that has been carried out on cosmology with intensity mapping of 21 centimeter line or H1 intensity mapping. But that's not all. There are also other emission lines like rotational lines of carbon monoxide or ionized carbon, which you can use to probe the large-scale structure. So this is basically the overview that in addition to the CMB at the very early stages, we can also probe the early universe via three-dimensional map of the large-scale structure as probed by galaxy surveys or intensity mapping, potential intensity mapping surveys. So what do we want or what do we know about physics of inflation and what do we hope to learn more about? So from the latest measurements of CMB by Planck, we know that the primordial fluctuations have a nearly scale invariant spectrum, which is usually characterized in terms of this parameter ns. And the plot at the bottom shows basically the constraints on the primordial tilt versus tensor to scalar ratio. And as you can see, it is well described by nearly scale invariant fluctuations. We know that the fluctuations are nearly Gaussian distributed, and deviations from Gaussianity would tell us about field content and dynamics during inflation. We hope that the next generation large-scale structure surveys will tell us more about the level of non-Gaussianity. Furthermore, detection of gravitational waves will tell us about energy scale of inflation, and in this case, the next generation CMB experiments are expected to do the best. So the focus here would be on learning more about non-Gaussianity of the primordial fluctuations via their imprints on large-scale structure. So to set a notation, let's say if we have a random field, like here characterized in terms of phi, which I would use it to refer as primordial fluctuation. If it is Gaussian, its statistical properties are described only fully in terms of the power spectrum. If the field is non-Gaussian, you need to include higher order correlation functions. it's conventional to just characterize this primordial bispectrum or in terms of a scale-independent amplitude and a shape. So when we talk about searches of primordial non-Gaussianity from a given survey, we are talking about constraints on the amplitude of primordial bispectrum of a given shape. Different shapes can tell us about different models of inflation. In particular, a shape that is of a lot of interest is what is referred to as local shape, which phenomenologically can be characterized in terms of a quadratic coupling or quadratic correction to the Gaussian field. And it's interesting because you expect that in single field inflation models, local shape non-Gaussianity or local shape primordial bispectrum should be suppressed. So if you detect FNL of order unity, that will be a strong evidence or a strong indication for multi-field inflation models. Now, as we all know, this primordial bispectrum will then leave an imprint on both radiation and matter distribution. Most naturally, it would lead to higher order statistics of radiation and matter field. And here, these are the snapshots of simulations on the left for CMB, on the right for dark matter distribution. For simulations with Gaussian inertial condition of FNL 0 or non-Gaussian inertial condition, so that, of course, these FNL values you see are huge, but this is just to exaggerate the impact that the primordial non-Gaussianity have on the matter and radiation fields. Now, in addition to this three-point function, of course, as we know probably, is that there would be an extra impact or extra imprint on bias tracers. In the absence of primordial non-Gaussianity, we know that, let's say, galaxies or quasars are bias tracers of dark matter. On the largest scales, these biasing relations can be parameterized by a constant. If you have now, in the absence of primordial non-Gaussianity, the long and short wavelength modes are not coupled on large scales, but when you have, let's say, local shape non-Gaussianity, this will introduce a coupling between large and small scales, so long and short wavelength fluctuations. And this coupling will change the amplitude of the short scale fluctuations, and this change of the amplitude of short scale fluctuations will translate into a change in the biasing relationship between a tracer and dark matter. And this is what is referred to as a scale-dependent bias, which was first measured in this paper by Dalal et al. In 2007. And here it's I'm showing basically what is showing in this plot is a cross-correlation of halo matter power spectrum, which would show basically the scale-dependent correction that I discussed before. So as you can see, for different values of FNL, positive values will enhance the power on the largest scales, while negative values will suppress the power. So this signature is used to constrain FNL from the current generation of galaxy surveys. So as you remember, the constraints from Planck are 1 sigma errors on FNL of about 5. And the current constraints from power spectrum measures from SDSS survey and EBOS survey are rather weak compared to the current CMB data. It is expected that these constraints are going to improve in the near future. So with that, let me kind of take a minute to say, okay, so this is very interesting because as we know, it's very interesting that the primordial non-Gaussianity would also leave an imprint on 2-point function, which in principle is easier to measure than the 3-point function. So then you can ask, okay, what is the maximum amount of information I can extract from power spectrum in the case that I had idealized measurement? And this was an interesting question that was addressed in this paper in 2014. So in the plot, there are a few different lines, but let me just draw your attention to a couple of lines. So these are error bars on measurement of FNL as a function of maximum redshift covered by your survey. And the yellow dashed line show the case where we only have a single tracer. So let's say galaxies or line intensity or what's or not. But we have a survey that covers basically all possible halo masses, which is idealized case because we would not be, okay, so let me first, take a step back. So let's first focus on the single tracer case. Let's say we are looking at a certain type of emission line galaxies that go all the way up to redshift 10. And of course, the constraints on FNL plateau at some redshift. So going up and higher into the redshift, you cannot go beyond the cosmic variance limit, which is about 0.1. Now, the other lines basically show the impact of having multiple tracers. Now, here in this case, in this forecast, multiple tracers were characterized in terms of minimum halo masses that you are observing. So if you're talking about minimum halo mass of 10 to the 8, which is this teal line, the lowest sigma FNL value, that is if you were able to measure all the halos above 10 to the 8 and you could distinguish between them, so you could perform multi-tracer analysis with all of these halos. So kind of the conclusion from this plot I wanted to draw was that in order to improve the constraints on FNL beyond what you can achieve with a single tracer at lower redshift is either to go to higher redshifts, but then also combining it with using multiple tracers, or you can look at higher order statistics. And in this also, it's interesting to notice that from this type of study, we learned that an optimal kind of survey to constrain FNL is actually a deep, wide, multi-band imaging survey, not a spectroscopic survey. And in that sense, something like SphereX, which has about 100 bands in near infrared, seems very promising to constrain FNL. So now here, let me just close this introduction. Maybe I should, before I go into the results I wanted to present, let me just stop and ask if there is a particular question. Okay. All right, so now let me, so the first thing I'm gonna talk about is basically how we can use high redshift tracers, and in this context, it would be line intensity to probe FNL. And in the second part, I will discuss about high order statistics, mostly in the context of galaxy surveys. And in the third part, I would, if I have enough time, I will discuss about some of additional effects that we have to account for when trying to use two-point function, either for galaxy surveys or for intensity mapping when trying to constrain FNL. So what do we mean by line intensity mapping? So basically, unlike the galaxy surveys where we observe individual galaxies, we can also measure the cumulative light from ensemble of sources or the intergalactic medium. Now, the spatial fluctuations of the line intensity would give us the spatial distribution, while the frequency of the line will give us the redshift. So the combination of the frequency and the spatial fluctuations will provide us a three-dimensional map of the large space structure. And there are various emission lines you can consider for performing intensity mapping. Of course, we know more about 21 centimeter, which corresponds to spin flip transition for neutral hydrogen. But additional lines like CO correspond, for instance, CO is a rotational line of carbon, which is which would correspond to multiple rotational lines. So there are CO basically J to J-1 lines. And then the C2 line is corresponding to ionized, to the fine transition of ionized carbon. And in terms of the frequency of these different lines, just to remind you that while the 21 centimeter is in megahertz regime, these CO and C2 lines are in the gigahertz, so in the hundreds and thousands of gigahertz. So they are millimeter and sub-millimeter lines compared to 21 centimeter. Now, so just to tell you that, as I said, there are multiple lines. So this plot, I just wanted to show you that there is basically there's a host of several emission lines. Now, some of them might be more useful for probing a given cosmological parameters, but then there are also subtleties in how you use these different lines, given that in a given frequency you would observe multiple lines and so on. And this is shown kind of in this plot where I'm showing the mean line brightness temperature on the vertical axis versus the frequency of the line. And as you can see from the left to right, you start from various rotational lines of carbon monoxide, and then we have the C2 line on the range of 1,000 gigahertz, and lower amplitude lines like oxygen lines and so on. So, okay, and now why is it interesting now? It seems a bit maybe too futuristic, but just to say that, that there is a growing interest in these lines apart from 21 centimeter. And here the diagrams basically show a range of completed, running, funded, and proposed surveys that are going to probe intensity with different lines. And then this interest seems to be growing, but the surveys are more at the Pathfinder stage. So it's interesting to kind of understand what kind of surveys are best fitted for probing cosmological parameters. And that's kind of what I'm gonna talk about. So going back to the issue of non-Gaussianity, as I showed before, the impact of this local non-Gaussianity is enhancement of power or suppression of power on large scales, and that the same as you would see it for galaxies, you would also see the same signature for any other biased tracers of dark matter, and in particular line intensity is also a biased tracer of dark matter. So here on the right, I'm showing the power spectrum of CO rotational, the first rotational line of CO at redshift 6, and various lines here. The dotted red one is the shot noise contribution for this power spectrum, while the solid blue line is the total power clustering power spectrum, including the contribution from non-Gaussianity, let's say with FNL of 6.5. And the blue dash dotted one is the instrumental noise. Now, so the first question I think one can ask is, okay, let's just do a simplistic, or not simplistic necessarily, but let's do a basic Fisher forecast and see if these lines can give an interesting constraint on FNL, assuming specific survey setups. And this was what we studied first. Was let's look at the CO 1 to 0 and C2 from surveys that are basically similar to what is on paper now, meaning that for C2 we took the survey like PIXI, which is a CMB proposed CMB experiment, which is also able to probe intensity, C2 intensities. And for CO we took loosely a survey like COMAP, but improving certain aspects of COMAP in terms of the sky coverage and redshift coverage. And then recently we also looked at other CO rotational lines, and it turns out CO 3 to 2 would be most interesting one for FNL. So this will just tell us that, okay, we are able to constrain sigma FNL of order unity, so there is interest there. But you can also show that now if you combine this with galaxy surveys, in particular with something like LSST, you can push down this FNL to below order unity potentially. But then there are a lot of questions to answer before you can take these forecasts seriously. In particular, the first question we wanted to understand was, going beyond these specific survey designs, can we find what is the optimal survey and instrument design to get FNL of order unity or better? And this will mean characterizing the requirements on sky coverage, redshift range, instrumental noise, and so on. How do these constraints depend on the modeling of the signal? And in particular, there is uncertainty in the model of the luminosity of the line, in addition to other ingredients. And then, of course, the big elephant in the room for line intensity mapping surveys is how well we can characterize the foregrounds and instrument systematics, and what's their impact on parameter estimation. And in the context of constraining non-Gaussianity from power spectrum, this has a very important role, because one of the impacts of foregrounds is contamination of the largest scale modes, which, as you saw, are very important in constraining FNL from power spectrum. And then there are also other questions that you can try to investigate. So let me just focus on the first, on the first and third point on that list, which the first one is instrument and survey design. So what we said was, okay, let's say that we parameterize our instrument and survey design in terms of certain free parameters. So Pn would be the instrument noise, F sky is a fraction of sky covered by survey, delta Z is a redshift range covered by the survey. And we need to make an assumption of the minimum and maximum, or the smallest and largest scales that a survey can probe. And those are determined on the smallest scales by the instrument characterizations like antenna size, resolution. And on the largest scales would be largely dominant or determined by foregrounds. And what we wanted to understand was, given if we try to minimize the cost of a survey, and for the cost, we would say the cost of a survey is determined in terms of the frequency range, the total observing time, and the number of beams. So if we have a fixed cost, what is the best value of FNL that we can constrain, and what would be the corresponding, let's say, value of sky fraction, or the frequency range, and so on. So this is what is shown on the plot on the left. So from the bottom to the top, on the vertical axis, we have F sky. N oct means it's a frequency. It characterizes the frequency range covered by a survey. So it is the frequency range in units of octave. And then the third one is median redshift, and the top one basically is the cost of a survey. So this N beam, N oct, and tau integration. And the important thing we draw from here is that potentially we can achieve sigma FNL 1, but one important ingredient is that we need a very broad spectral coverage for a survey. But the sky coverage is not too demanding, let's say. If you have a broad spectral coverage and the sky coverage of at least about 10% of the sky, you could potentially achieve FNL over the unity. And then you can get more sophisticated and ask how stable is this optimal point that we found. And this is what is this very busy set of plots is showing, but just without going into the details of the plots, but what we basically said was, now let's see if we perturb any of these parameters in the optimal setup and see how much the optimal setup will shift. And the answer is, like, in terms of sky fraction and the frequency coverage, the impact of shifting the parameters is not that large. So if you shift the parameters by about 10%, this will produce a shift of 5% in the constraints. And so just to to summarize this part is that it seems like when you want to design the survey, first thing you have to worry about is the frequency coverage, in addition to sky coverage that we always talk about. So what matters is the total co-moving volume and not only the sky coverage. Now, then the first thing you can ask is that, okay, great, you can go to FNL over the unity, but here you assumed that the foregrounds are smooth, which is the assumption we made, but how sensitive you are to the fact that the foregrounds may not be smooth. And that dominantly will show itself in the change of the largest scale modes that we have in the survey. So as was shown in this paper and a series of other papers, the subtraction of the foregrounds, for instance, for the C2 line can give rise to contamination of the largest scale modes. So in particular, if you decompose the modes in parallel and perpendicular to the line of sight, parallel to the line of sight, position-dependent errors in the estimate of the amplitude, basically position-dependent errors in the estimate of the amplitude of the signal will induce loss of large-scale modes actually perpendicular to the line of sight. And we would characterize it in terms of this parameter theta max, which is related to angular diameter of a survey area. Now, but that's not all. We also lose the largest scale modes along the line of sight, and this is due to the spectral response of the instrument to the continuum. Basically, we characterize it in terms of this parameter eta min, which characterizes the range of frequencies over which the response of the instrument to the foreground is smooth. Now, what I want you to remember from here is that these two plots basically show you how the constraints on FNL degrade as you change these two parameters, the eta min and theta max. As you can see on the left plot, this eta min can be also seen in terms of the frequency range over which the response is constant or is smooth, basically. So this delta nu max over nu observed. So as you can see that if you go from having basically two units of frequency over which signal is smooth to one unit, then the signal on the FNL can degrade by 10%. Now, if you go from 2 to less than 0.5, the signal can be degraded by about 50%. So this is now just an effective way of characterizing the possible degradation of the signal. But of course, if you, for a given survey, you need to model the foregrounds accounting for a specific instrument and survey design. Now, the other question is that, okay, so we learned about optimal survey design and effectively how the foregrounds can affect our constraints. Can we understand how the current design survey designs sit in this landscape that we, or parameter space that we probed? And here is what we find. So we would look basically at this survey specifications like COMAP phase 2 or something like next generation VLA for CO's line, and to something like PIXI or Origin Space Telescope for C2. And as you can see, so the issue is that all of these surveys have limitations. For instance, COMAP2 has a small frequency coverage, while VLA has low pair mode sensitivity. On the C2 side, PIXI has limited sensitivity in high redshifts, while Origin has redshift and limited redshift and sky cover. So that means that none of these actually is able to go below FNL of 2 in the ideal case. But the point is that once you understand what are the characteristics you need to improve, in principle, with something like Origin, for instance, if you can have the larger sky coverage and redshift coverage, you are able to go to FNL of below 1. Now you can say, okay, this is all good, but it's too futuristic because all of these surveys are not in the very near future going to happen. So then the interesting other thing is that, okay, so what are the expected limits on FNL you can get from surveys that are more on the horizon? And it seems like error bars of order sigma FNL of 3 are more achievable, and in that respect, a 2-year survey with sky fraction of, let's say, 3% could achieve such a constraint on FNL. And interestingly enough, these are the type of surveys that you can construct that people have been interested in order as surveys to cross-correlate with 21 centimeter intensity by surveys like HERA. And in that context, these surveys are taught for validation of 21 centimeter line as having cosmological origin. But with what we are finding is that such a survey also can be used to constrain FNL. So this is a science at no cost, basically, with a survey that is not taught to constrain FNL. So I think this is quite interesting. So kind of to summarize this part on intensity mapping, I think is while achieving FNL below order unity is possible, but it seems challenging and also farther on the horizon, while achieving FNL of order a few, which, just to give you a reference point, would be similar to upcoming galaxy surveys like Euclid and DESI, is potentially on the horizon, and it may be possible to achieve it even with non-specifically designated surveys, like the results that I just showed before. But it's critical to have broad spectral coverage, and an important thing important ingredient that needs to be refined is the modeling uncertainty and its impact on the parameter constraints. And then the question is how much the cross correlation with other surveys can improve on these constraints. And finally, things that can be thought of is that, of course, power spectrum is the lowest order statistics, and to constrain FNL, higher order statistics like Bispectrum potentially can be very powerful. So going beyond the power spectrum analysis is very important. So with that, I would now want to move to, basically based on this last point of going beyond the power spectrum, I would like to tell you a few words about basically the potential of constructing new estimators to extract information from 3-point clustering statistics. And this would be in the context of galaxy surveys, but in principle, all I'm talking about is also applicable to line intensity or any other large-scale structure tracer. And this would be, this optimal estimated is what I would refer to as weighted skew spectra, which in a second will become clear y is referred to as following. So, up to here, of course, a lot of our effort in cosmology and in probes of large-scale structure has been extracting cosmology from two-point statistics, either in real space in terms of two-point correlation function or in Fourier space as power spectrum. But there is significant amount of information potentially in higher order statistics, but it is challenging to extract information from higher order statistics. And the challenges are both theoretical and computational. On the theoretical side, modeling of the signal is difficult. Now, since large-scale structure is nonlinear, all the difficulties that are there in modeling the power spectrum are also there for the bispectrum and even more stringent. But that's not all. On the computational side also, because now we have an observable that depends on multiple variables, in the simple case depending on 3 wave numbers instead of 1 wave numbers, there are a large number of combinatorics, and this will make it challenging to compute the signal and the error, as well as the actual estimator. There have been alternative strategies taken in addition to just directly going for the measurement of the bispectrum or trispectrum and so on. And that is to construct either to construct proxy statistics, which capture fully or partially the information in the bispectrum in an optimal way that is optimal in constraining certain set of cosmological parameters. And examples of those are line correlation function, integrated bispectrum, weighted Skew-Spectrum, and etc. The other approach has been trying to compress the data into a few numbers, basically, that are again constructed such that they are optimal in constraining cosmology. I'm going to focus on the first approach, basically, and then, as I said, I would discuss about this proxy statistics, i.e. the weighted Skew-Spectra, and how we can constrain cosmological parameters from it. So the idea here is that if when we are measuring the 3-point function, let's say on the right, I'm just showing a snapshot of n-body simulation. So imagine you want to now measure the 3-point function of this field. Instead of measuring this 3-point function, if you're interested in the parameter that appears as the amplitude of this 3-point function, you can also construct a power spectrum-like object that will carry all of the information that is there in the bispectrum on parameters that appear as amplitude. And this is, of course, not a new idea. This was used for CMB in terms of this Skew-Spectra, and then later in this paper of Schmidt-Wood et al. For large-scale structure. And it was shown that all the information of gravitational bispectrum can be captured in terms of 3 estimators. So they are called the Skew-Spectra. So these p hat, delta 2, delta. And in practice, what you would do is you would take your observed density field, you would square this field with some given specific weight functions that would correspond, for instance, to square of the density, or a combination or a product of displacement field and density gradient, or the tidal tensor. And then you correlate the second order or quadratic field with the original density field, and this captures the information in the bispectrum. Now, if you have primordial non-Gaussianity, then you can show that along the same lines, you can extract the information on the amplitude of primordial bispectrum by constructing a 4th Skew-Spectrum, which now is like the correlation of, so this delta over m is the density field divided by the transfer function. So basically you take your observed density field, filter it with inverse of the transfer function, and that field is basically like a gravitational potential, and then you correlate this gravitational potential with the other fields that you have. So now, let me also say that what we did, or what was done in this paper of 2014, was to construct this quadratic field and correlate them with the original field, such that the new estimator you are building, this Skew-Spectra, capture the information in the 3-point function of the density field. Recently, it has also been proposed that instead of correlating this quadratic field with another density field and extract 3-point function information, you can build a quadratic estimator in terms of these quadratic fields themselves, and then you can correlate quadratic fields with each other with the linear density field, and in this way you can extract not only the information in the 3-point function but also the information in the 4-point function. So now, once you basically, now you can compute what are these new skew spectra, and this is a bit of a busy plot, but the point here is to guide your eyes to the lines to look for. So basically, these different terms are showing these 3 different types of skew spectra, as well as the primordial one, so the 4th one here. And if you look at the dashed lines, they would be all the skew spectra that come basically that have a proportionality factor that is like cube of the linear halo bias. So these different terms are characterized in terms of the amplitude parameter combinations that appear in front of them. So in that sense, when you combine these different skew spectra, you would get all of the information that is there from the bispectrum on the bias parameters and on the FNL. Now, as you can see, these skew spectra are not independent of one another. They are not orthogonal. And in fact, many of them are indistinguishable from one another on large scales. So while in what we did, I will show that we consider them as 3 independent or 4 independent observables, but in practice, you would probably not want to use all of them, but you would want to build effective, more optimal combination of these spectra that will capture all the information. Now, these skew spectra, as I said, they are not independent of one another. So when you want to use them in a full data vector, you have to also account for the fact that the estimators are correlated with one another. And this is what we are showing here. And this is basically the covariance matrix of the data vector, including the 3 of these skew spectra, which are characterized in terms of L0. L0 would be the skew spectra that was quadratic density field correlated with another density field. L1 would be displacement field and derivative of density field correlated with another density field. And L2 is the tidal shear field, the skew spectra built out of tidal shear field. Now, you might wonder, okay, does it really matter if you account for all of these covariance terms correctly? And it turns out it does matter. So first of all, let me show you this plot that shows that the information in this skew spectra is exactly the same as the information in the bispectrum. So the blue and the purple lines show the cross-spectrum constraint versus bispectrum on linear second-order bias parameters, as well as the correction to shot noise. But then in getting this exact agreement, it is very important to account for the covariance correctly. And this plot is showing basically the constraints from combination of these skew spectra. If you only account for Gaussian piece of the covariance, neglecting all the off-diagonal thing, or if you account for the full covariance. So not only you underestimate the errors, but you also alter and change the parameter degeneracies if you disregard those constraints. Now, the thing that you might be interested is, okay, I discussed that in addition to the 3 skew spectra that characterize the gravitational bispectrum, you can construct the 4th one that characterizes the gravitational potential, and you can use that to constrain FNL. And that's what these plots are showing, that if you look at bispectrum of local, equilateral, or any other shape, and we are interested in constraining its amplitude, either using the skew spectra in blue or bispectrum in purple, you get constraints that are in very good agreement. So, but this is like a starting point in a sense that in construction of these skew spectra, they were constructed such that they are optimal only for the parameters that appear like amplitudes of the bispectrum. So they are not, if you now run the analysis with the skew spectra for cosmological parameters and compare it with bispectrum, they would not have the same information. So one needs to extend the spectrum for to include optimal weights that are constructed such that the skew spectra will have the same information as the bispectrum. We showed that accounting for the full data vector covariance is necessary. And what we have not included is the fact that all this is computed for real space measurements of the bispectrum or skew spectrum, but in reality we only measure things in redshift space. So one is to extend this estimator to include redshift space distortion, and that is what we are currently working on. So with this, I take the last 5 minutes to tell you some more recent work, which is, okay, so we talked about power spectrum, how we can use a power spectrum to measure FNL. We talked about potential of higher order statistics, and in particular, building new estimators for higher order statistics. But is there something that we are not including and it's important to include? And in that sense, I would only talk about the impact of modes that are larger than the size of survey on the modes within the survey. So now, up to here, as I said, we talked about clustering statistics of fluctuations that are inside a finite volume survey. Now, but we also can have fluctuations that are larger than a size of a given survey. And what is important to ask is, while we cannot directly observe those long wavelength modes, but would they impact the measurements of clustering statistics inside the survey? And this is something that people have studied extensively. Of course, you can say that how I can parameterize this very long wavelength mode in terms of in derivative expansion, basically. So let's say if you have a survey centered at position x0, you can expand the gravitational potential in terms of a constant and second derivative terms. Well, I have dropped the first derivative because it's unphysical in this case. If you have Gaussian initial conditions, the only long wavelength mode you have to account for is a long wavelength density mode and the tidal field. If you have primordial non-Gaussianity, the constant gravitational potential is also physical, so you have to account for the long wavelength gravitational potential. And this long wavelength mode would induce coupling between super and subsample modes. And this is only due to nonlinear gravitational evolution, meaning if there was no gravitational evolution, there would be no coupling between these different modes. Now, physically, what is the impact of these super survey modes? Basically, they have two effects. So if you have a survey of a finite volume, like is shown in this orange line, you measure fluctuations inside this volume. But if you have large wavelength fluctuations, like the red line, the impact that it will have on the modes inside the survey are twofold. It will change the growth of structure. So it will cause enhancement or suppression of growth of small structure. And it will also cause a dilation, meaning it will cause more contraction or expansion of co-moving volume. Not only that, but there's also an additional effect that the mean number density of object inside your survey would also change. And in reals, there's a difference between making measurements in real space and in redshift space. If in real space, because the power spectrum is isotropic, only the isotropic part of the larger scale modes will contribute, meaning the larger scale tidal field has no imprint. While in redshift space, because the statistical isotropy is broken, now a large scale tidal field would also affect the subsample modes. So, this you can now compute basically what is the impact of this large scale modes on the small scale fluctuation in the context of, for instance, response function. So the p hat here is a power spectrum of small scale fluctuations in the presence of the larger scale modes, which are basically represented by this delta 0, phi 0, and delta 2. Delta 0 will be the larger scale density, delta 2 is large scale tidal field, and phi 0 is large scale gravitational potential. And these response functions have been proposed that it can be computed from squeeze limit of the bispectrum after angular averaging. And the squeeze limit is the limit where one of the sides of the triangle defining the bispectrum is much smaller than the other two. And if you do so, you can show that, as I discussed before, that the impact of these larger scale modes can be understood in terms of a growth part, which changes the growth of structure, and in terms of a dilation. So you see that the dilation terms are basically derivatives of the power spectrum or transfer function with respect to k. And when you compute the primordial response to the gravitational potential, you see that it only has the growth part and no dilation term. And that is understandable because local non-Gaussianity only induces change of the amplitude. It doesn't cause any dilation. And the other effect that I talked about, which was change of the mean number density measured inside the survey, should also be accounted. Now, putting all these things together, now you can look at the shape of the responses. On the left, we are showing the response functions for density and gravitational potential. These are real space, so there is no response to tidal field. And on the left, we are showing the response for a galaxy sample that is at low redshift, and this would kind of loosely relate to a sample of, let's say, emission line galaxies from DESI, while on the right, we are showing the response functions of a high redshift sample, which would correspond loosely to the quasar sample of DESI. Now, as you can see, the responses for different samples, depending on their biases, shot noise, and redshift, have different shapes and also different relative amplitude. But the important thing to notice is that as I showed before, the response of the short scale fluctuations to the long mode density will also have a contribution from a non-Gaussian initial condition, and that is shown by the difference between the solid and dashed blue lines. Then you can correspondingly compute the responses in redshift space. And now, as I said, because of the anisotropy of the power spectrum, there is also response to the tidal field, and that is shown here in green. And again, the left shows the responses for low redshift, while the right shows the responses for high redshift samples. And then you can put all these together and say, okay, great. So we computed them. Should I care about them when I constrain FNL? And so for that, you do a Fisher analysis as the first step. And in this case, we would consider the amplitude of this long wavelength mode as an unknown parameter that we would take as a free parameter and marginalize over it in constraining FNL. And here is what you expect for the constraints on FNL. So this is the constraints for the high redshift sample. On the left, and the left and right plots will correspond to assuming the long wavelength gravitational potential having positive or negative value. Remember that we don't know the value of this mean gravitational potential, so it can be positive or negative values. And the takeaway from this plot is that if you look at the blue and the red curves on both plots, the blue correspond to the usual measurement of the power spectrum, neglecting the supersample modes, while the red correspond again to the usual power spectrum measurement, assuming that you have a strong prior on the value of the linear bias. Now, on the other hand, if you look at the orange, is if you account for the supersample mode and you impose no prior on the amplitude of the large scale mode. So you just leave it as a free parameter and you assume no prior knowledge on it. And doing so impacts the constraint on FNL significantly if you limit your analysis to only maximum K of below 0.1 and about 10%, let's say, if you push your analysis to 0.2. But now the interesting thing is what happens if you have actually prior or additional information on the value of this long wavelength mode and the linear bias. And in that case, it's interesting that you can actually achieve improvement in the constraints on FNL if the value of this largest scale gravitational potential is negative, and it has to be rather large negative in order to see a significant improvement. Now you can say that, of course, those large values of a mean of the gravitational potential are also the most unlikely ones if you assume a Gaussian distribution. Now the improvement is more interesting, I think, or if you have a low redshift sample, because here you can see that if you include the long wavelength mode and impose priors on delta L and also on the bias, you can improve by at most about 30% on the constraints on FNL for the low bias sample. But of course, this said is that, as you can see, the low bias sample of this sample corresponding to DESI sample is less interesting to constrain FNL because of its low bias. It's kind of, although you can make a improvement for the low bias sample, but overall the high bias sample was a better candidate to constrain FNL. So with this, let me just put out this conclusion that from this part, the conclusion was that it is including the supersample mode with no prior, it causes degradation that is not significant. Let's say now it depends what you call significant, but it's about 10% degradation if you push your analysis to Kmax of 0.2. Even if you have a mild prior on the amplitude of the long modes, allows you to recover the constraints on FNL. But notice that while I showed in these plots only constraints on FNL, not imposing any prior on the long mode will degrade the constraints on linear bias. So if you want to constrain other cosmological parameters that are degenerate, for instance, with linear bias, including the long wavelength mode, degrade your constraints on linear bias significantly. And as I said, for low redshift, high number density samples, such as DESI ELG, imposing a prior on B1 can result in about 30% improvement on the value of FNL if the fluctuations of this gravitational potential are the rarest 5 sigma fluctuations. So, so I think with that, I would stop here and take any question.
Yes, thanks a lot. Great talk. Before we take the questions, let me just conclude the live stream on YouTube. So for all the folks watching this on YouTube, please, if you have questions, you can write them in the comment section. I hope you enjoyed the talk and see you next week.